Hello. In the last video, we're talking about turbine and compressors and what are the specific formula for them in terms of mass conservation and energy conservation. So here's a recap on the equation. For turbine, we know turbine will generate the work, so that's work out over dot, which means divided by time. That's going to be equal to mass flow rate. It's going to be fine. Initial minus final, because initial has higher enthalpy, have higher energy. As compared to for compressor requires work, so it's work coming in. That's going to be the final H2 minus H1, because compressor, you require work to increase energy of the fluid. Okay, so now we're going to look at this example. You have turbine, high pressure of air. So remember we're talking about whenever we work on open system, it's very good idea to draw the device and just simple cartoon sketch of it. So for turbine, we know turbine is going to be from smaller end to the bigger end, and turbine so comes in here and come out here and you generate work, right? Oops, it's going to be work out. Okay. So now we're going to start to add those conditions that's given onto the sketch. So it's air, first of all, this is air. So it's ideal gas. That comes in at 1300, so we're going to put 1300 here, that's the inlet. Then going through steady flow, which we'll make assumption on all of those open system device as steady flow, which means does not change over time, and adiabatic, which means there's no heat transfer, right? Q equal to 0. We kind of made that assumption when we arrived those equations here. And to the exit at 660 K, that's going to be the outlet temperature. Then we ask to calculate the work done per unit mass. Okay, work is energy, so it's kilojoule. Work done per mass, so that's going to be per kilogram. That's what we are solving. This is something first we saw, maybe. It's work done per mass, how much kilojoule per kilogram of air. So using 3 different methods. So this first one using temperature dependent data. That is using table A17, right? Ideal gas table. And then average CP, okay? And then using 300. All right, let's go. So if this is a turbine, our first equation, we're going to list work out equal to mass flow rate times H1 minus H2. Let's think about the unit for a second. Work out with a dot. Work out, that's going to be unit of kilojoule per second, since it's with a dot, which means divided by time. And mass flow rate going to have a unit of how much kilogram pass per second, right? H1, H2, they're going to have a unit to kilojoule per kilogram. So now let's think about it. Then times together, kilogram canceled. You indeed get kilojoule per second on both sides of the equation. But we are asked to find work per unit mass. So which means it's kilojoule per kilogram. Well, that happens to be your work out over mass flow rate. That's going to be our kilojoule per second divided by kilogram per second. That's going to be our kilojoule per kilogram. So the next time when we saw something about energy work per unit mass, we know they're asking about this. So that will be also equal to H1 minus H2, right, from this equation. So essentially, this problem is basically ask H1 minus H2. All right, so the next step we're going to thinking about, how do we find H1 minus H2? It is indeed air, and this is similar to what we're talking about delta H. Delta H is final minus initial. So that's the only difference. Here's 1 minus 2, here's 2 minus 1. So it's going to be using 3 different methods. Method number 1, if we're using table A17, okay. I'm actually going to erase this because I might confuse. So table A17, we're going to find a workout per mass flow rate. That's our H1 minus H2. So what's our H1 at 1300 K minus H2 at our 660 K. Let's go ahead and get our tables out. A17 1300. We're reading H, so that will be this value. Oops. I think I have to minimize that. That's 1395.97. And at 660, we're pretty lucky they have that one. That's 670.47. So when we calculate that, we will get 725.5 kilojoule per kilogram. So that's our first answer using table A17, using tabulated data, which is time dependent, which is the temperature dependent data. Then the next method, method 2, we can use average temperature. So in this situation, this workout over mass flow rate is equal to H1 minus H2, right? And then if we were to using our CP, because it's H enthalpy, we have to use CP. Again, if it's U, we're going to use CV. So CP at this average temperature. And here, since it's 1 minus 2, we're going to use T1 minus T2. Okay. Now let's take a look. So where do we find average temperature? We know the T average is going to be half of initial plus final. Initial is 1300 K and end temperature is 660 K. Then we divide by 2. Let's see what's our temperature going to be. 1300 plus 660 divided by 2. That's 980 Kelvin. So now we just need to find CP at 980 Kelvin. Then we're going to go back to our table, A2. A2B to be more exact. So table A2B, we can find our CP at 980 for air, so for this column, 980 is between those two values. Well, looks like we need to do linear interpolation. So let's do a quick linear interpolation for this. So if we decided to put delta Cp as the y and delta t as our x, that's going to be our slope. So our ending point, we're using 1000 minus 900 because that's the two extremes wrap around 980. And corresponding 1000, our Cp is 1.142 and the 900 is 1.121. That's going to be equal to, if we were continue using 1000, and so 1000 minus 980, then we will be using 1.142, and for 980, we do not know this value. That's what we are solving, right? Cp at 980. So with that, we can calculate our Cp. Without further ado, I'm actually just going to write down the answer for Cp. That's 1 at 980. That's going to give us 1.138. Okay. And that's unit of kilojoule per kilogram per Kelvin. So knowing that, we can go back to, I think we're done with the table. We can go back to solve this now. So we're going to write down 1.138 kilojoule per kilogram Kelvin. Then times T2 minus T1. T1 minus T2, 1300 minus 660. That will give us a value of 728.3. The unit, this is Kelvin, so cancel out kilojoule per kilogram. Work per unit mass. That's what we are solving, right? That's method number 2. All right, what's the last method they want us to use? They said we did the first one, table A17, using the ideal gas table, and we also use the average. Now the last one is 300. So method number 3. So we still have workout over mass flow rate out. That's going to be equal to Cp. However, we're using 300 Kelvin. Since it's H1 minus H2 here, that means T1 minus T2. So the only difference between this method and method number 2 is Cp value will be different. If we're going back to table A2A, we'll get the value as 1.005. I can quickly take that out here to show. For air, right, at 300 Kelvin, and Cp is 1.005, that value. And then T1, it's also our 1300. T2 is 660. Then when we calculate that, you see that's the only difference between those two. It's just that value and this value are different. Okay, so when we put those values in, and our answer is 643.2 kilojoule per kilogram, work per unit mass. So quick wrap up. So you use 3 different methods to solve this turbine problem, and their answers are pretty similar. The first one is the most accurate answer because it's time-dependent data from a table, 725, and the second method, it's 728. It's close enough because we're using average temperature, and this average temperature is actually 980 Kelvin. So when we use 300 Kelvin, it's not that close to 980 Kelvin, and our value is a little off at 643. All right, so that's all for this example for turbine. I will see you next time. Maybe we'll work on one for compressor. All right, until then, bye now.